was the Dijkstra's algorithm. And the final operation that we are going to cover is the minimum spanning tree problem. In the shortest path problem, it was a path planning from a selected source. The minimum path spanning tree is more like rather than considering a single source to one another destination, it was more about the network control problem. So if we select a certain node, how much will it cost to control all the vertices? So for example, we are going to select a certain node to install the logistics center. And these are all the buildings that the vertices are equal to buildings we have to cover to deliver our supplies. In that case, how much will it cost? And what would be the ideal path to control all the vertices, deliver all the buildings? That is the minimum spanning tree problem. All vertex coverage with the minimum cost. And this is often used in the telephone network design, electricity grid network design, TV cable network design, computer network design, and road network design. So it's being used many places. So another thing is that social network influence problem. For example, if we can measure the friendship strength between two persons, then we are going to have similar social network like this. And then given a certain politician, how much will it cost to control this whole social network? That's been another problem recently. To solve the minimum spanning tree problem, we can utilize the Prim's algorithm. So Prim's algorithm takes of course, the graph structure and the S as being the selected source vertex that we can start with. And then the thing that we want to do is that we want to start grow the covered nodes by adding another uncovered node from this side. So when you really start, the selected source is only at being the covered node size, and all the other nodes are not covered. And one by one, we want to add another different vertices into this covered node size. So when you want to select the uncovered nodes to add to the covered nodes, what you want to do, the thing that we want to care about is the edges in between. So edges between the covered nodes actually doesn't matter. Edges between uncovered nodes actually doesn't matter. What matters is that the edges between the covered nodes and the uncovered nodes, and we want to find the minimum values from the between the covered nodes and uncovered nodes, and we want to select that nodes being connected and put that thing inside of the covered node size. And then after putting that nodes 3 in the covered node size, uncovered nodes will be 4 and 5, and covered nodes is going to be 1, 2, 3. To understand this algorithm, better to look at the progress, how things being solved one by one. By looking at it, I think that you learn better. So let's start this example. So we selected this node 1 as our being logistics center, and we want to find all the nodes to cover all the edges, all the passes, all the edges to link all the nodes in this graph. So we have vertices 1, 2, 3, 4, 5 to cover, and already 1 is being covered. So E is the edge that are being used to cover. So here 1 is in the covered node side, and 2, 3, 4, 5 is uncovered on node sides, and 20 and 3 are the edges are connecting between covered nodes and uncovered nodes. And we want to find the minimum cost, and then we want to put that connected nodes inside of the covered nodes. So what we want to do is include 2 here. So we are going to put the 2 in the covered nodes, and all the other nodes as the uncovered nodes. And then the selected edge is being stored here, and it's going to be 1, 2. And after that, the edges connecting the covered node sets and uncovered node sets are 20, 5, and 15, and 6. 4 and 7, we don't have to consider it, and this we don't have to consider it. Between these, actually 5 has the smallest number. So it means that we have to add 4 in our covered node sets. So we are going to do like this. This is going to be our next covered node set, and this edge is being included here. Like this. This is being our covered node set, and this is being our uncovered node sets. Then this edge 2 are being selected to make the minimum spanning tree here. And the covered nodes, and between covered node sets and uncovered node sets, we have 6, 15, 7, and 20 edges that linked between these 2 different sets. 4 is not being considered because this is between uncovered node sets. Here, the 6 has the minimum value. It means that we are going to recruit node 3 for our next covered node set. So it's going to be like this. Then 2 and 3 and this edge 6 is going to be selected and put it in here. Like this. So uncovered, this is covered node sets like this, and this is the only uncovered node sets. And then to connect between 2 different sets, we have 4, 15, 7, and 20. Means that we have to select this 4, and 5 is finally being recruited like this. And 4 is going to be put in here. And then we finally covered all the edges, all the nodes. And we find all the edges to be used to control all the nodes. So by using these edges, we can reach to all the 1, 2, 3, 4, 5 nodes. And then we start this particular the spanning operation started from 1. If we just select 1 and put it at the root, then we have 1, and we have 2, and we have 3, and we have 4. and then we have 5. This looks like a tree structure. So this is being called minimum, as means that cost is minimum, spanning, covers all the nodes, and it looks like tree, so tree. So we call it minimum spanning tree. Again, time complexity looks like this. It's the same time complexity to the Dijkstra's algorithm. We are not going to prove this, but remember that we have h term here. Means that it's going to take b squared log b. So it's going to be pretty complex algorithm. So that's all I have for week 13. Here is the further reading. In this slide that I didn't give you any programming task. However, to be able to program this, you have to understand all the concepts. So please focus on understanding the concepts, and we are going to practice a little bit in the offline session how to program it. Okay, so thank you for listening and have a good day.